So we continue our discussion of entropy, which we saw is a measure of the disorder of the system, and more disorder generally means more entropy. Now, if you think of the definition of 0 Kelvin, it's a temperature at which all atomic and molecular motion is assumed to cease, and the entropy of that state is taken to be zero. It's a definition, doesn't exist, but we use it to idealize what would be the perfectly crystalline solid and consider the entropy of that perfectly crystalline solid to be zero and measure the entropy of solid, liquid and gaseous matter with respect to that state. So entropy in general increases as disorder increases. That is, a gas is more disordered than a liquid, which is in turn more disordered than a solid, and hence a gas has the more entropy, liquid has lesser entropy, and solid has even less entropy. And as temperature reduces, the entropy level is taken to be lower. Now, at the same temperature, if you have three systems, one being a solid, the other being a liquid, and the third being a gas, the gas has most entropy and the solid has the least entropy, with the liquid being intermediate. That is, among these three, between these three, that would be the entropy relation. Now, what is this entropy? We need a mathematical definition of entropy. How to define this mathematically, or how to define this quantitatively, so that we can use it for analyzing problems, and we'll see what is the utility of this quantity entropy that we are starting to construct. We begin by discussing an empirical observation that has been true for all the observations made so far in the context of thermodynamic analysis, which is the heat change divided by the temperature for a cyclic process has always been observed to be either less than or equal to zero. This is an empirical observation and it's called the Clausius inequality. The Clausius inequality was observed by the German physicist Clausius, and it is stated as the heat change, I write it in words, the heat change in a cyclic process divided by the temperature is always observed to be less than or equal to zero. Okay, the cyclic process. Remember, a cyclic process, it is something in which you have a bunch of intermediate states. You can have intermediate states. It need not be always 4. It could be multiple steps, but whatever the number of steps are, it has been observed that the net heat transfer for the individual steps divided by temperature is less than or equal to 0. This symbol, the integral symbol with a circle, denotes integration or summation over each process. What do I mean by that? If I have a process, that is, for simplicity, I'll say 1, 2, 3, 4, and then back to 1. Delta Q over T cyclic integral is practically equal to the heat change in process 1 to 2. Looking at the space, I'm just going to continue this next page. Delta Q over T cyclic integral is practically equal to the heat change in process 1 to 2 divided by the temperature at which this heat transfer takes place. I'll talk about the T in a second, plus I'll say T1, 1 to 2, actually I just leave it as T, okay. It's delta Q over T 1 to 2 plus delta Q over T 2 to 3 plus delta Q over T 3 to 4 plus delta Q over T 4 to 1. The Clausius inequality simply states that you can have any number of intermediate steps, but the net heat transfer divided by the temperature is always less than or equal to 0. Now what is T? Now what is T? T is the temperature at the boundary where heat transfer, it could be in or out, heat transfer can be in or out, heat transfer takes place. Okay, so if you have a system, okay, suppose there are sections in which heat transfer takes place, like it could be a heating element, it could be a cooling element, and let's say this is Q1, this is Q2. What I am referring to as T here is the temperature at this interface, temperature at this interface. Okay, so we would take Q divided by T at port 1, Q divided by T at port 2, and so on. And we define it this way because T is the boundary temperature at which heat transfer takes place. We define it this way because heat transfer usually takes place between a system and a heat reservoir that has either infinite capacity to provide heat or absorb heat. Now what do I mean by a heat reservoir? If you have, let's say, an engine, like for example, if you have a heat engine, so if you have a heat engine, what are the components? Your components are a step where you have a turbine that expands hot gases, okay, and then you have a condenser where you reject heat, turbine where you extract work, okay, you extract work, and then you have a condenser where you reject heat, and then there is a compressor, where you input work, okay, and then there is a combustor or a heating element where you supply heat. Okay, this is your simplest engine, and in this engine we always assume that this the heat source or the heat reservoir is at a fixed high temperature TH, and the heat sink or the atmosphere is at a fixed low temperature TL. Okay, so these are your temperatures at which the heat transfer takes place. TH and TL are the temperatures that I am referring to, are the temperatures at which I'm going to just rewrite this as I do in the class. I always underestimate the space. TH and TL are the temperatures at which heat transfer takes place. So when we talk about delta Q divided by T, it's either delta Q in at TH or delta Q out at TL. Okay, just for example. Okay, so Clausius found out that delta Q over T divided by temperature, delta Q divided by temperature is always less than 0 for any process. And earlier we discussed what is an internally reversible process. An internally reversible process is one which, when brought back to its original state, when the system is restored to its initial state, there is no change in the surroundings. That is, both the system and the surroundings are restored to the initial state without any change. Such a process is called an internally reversible process, and anything else is irreversible if it is not internally reversible. I'm sorry, anything is irreversible if it's not internally reversible. So it is found that delta Q over T for steps that are all, for a cycle that is composed of all reversible processes, is 0. 0 for a cycle that is composed of all reversible processes. For irreversible processes, or in general, this integral is less than 0. Okay. So you have this Clausius inequality is true for all processes with the condition that it is equal to 0 for delta Q by 0. The delta Q over T is 0 for a reversible process, and delta Q over T is less than 0 for a irreversible process. The quantity delta Q over T for an internally reversible process is what we define as the change in entropy. That is, entropy is defined as the heat change divided by the temperature at which it takes place, provided the process is internally reversible. Okay, So heat as units of joule, temperature as units of Kelvin. So uppercase S has units of joule per Kelvin. Okay, if you do the same thing for on a per mass basis, this would be delta Q over T internally reversible equals ds, where S will have units of joule per Kelvin per kg. Okay, so if one were to compute the entropy change delta S for a process that goes from 1 to 2, I'll draw the process. 1, 2. If this process were to be internally reversible, delta S, which is S2 minus S1, is 1 to 2 delta Q over T reversible, and the integral of 1 to 2 delta Q over T reversible. Now remember, some process can be internally reversible only if there is no friction, no rapid expansion, slow mixing, and no chemical changes or chemical reactions. Okay, internally reversible process is an idealization of what takes place in reality. Okay, so for an internally reversible process, or if there is a process which can be considered to be internally reversible, delta S is 1 to 2 delta Q over T reversible. If you look at figure 7-3, figure 7-3, you can have a process which is plotted as T in terms of T and S. Okay, S in kilojoules per Kelvin and T in Kelvin. Okay, you can have a state 1, you can have a state 2, you can have a reversible process between 1 to 2. Okay, and you can also have an alternate irreversible process 1 to 2. Okay, both between 1 and 2. Okay, there is the end state and the initial state, they are the same. If you think of 1 to be having an entropy of 0.3 and 2 to be having an entropy of 0.7, entropy being a state variable, delta S is S2 minus S1 because entropy is a state variable, and can be written as 0.7 minus 0.3 equals 0.4 kilojoules per Kelvin. Okay, this entropy change is equal to the reversible heat transfer between 1 and 2 divided by the temperature. Okay, that's the meaning of this statement. And T is not the temperature at 1 or at 2, it's the temperature at which heat transfer takes place. Temperature at which heat transfer takes place. It's not T1 or T2. Not T1 or T2. Okay. So as a special case, if we have an internally reversible, in this class at least you can think of internally reversible as shorthand for frictionless. Okay, isothermal constant temperature heat transfer process. So in that case, delta S is delta Q over T from 1 to 2, which is internally reversible, and we are going to say isothermal, so we are going to say the temperature is T naught, 1 to 2 delta Q over T naught internally reversible, or in other words, we are going to write this is 1 over T naught 1 to 2 delta Q internally reversible. You can write this as 1 to 2 Q divided by T naught. Now I keep telling you, what is this internally, or what is this delta Q internally reversible? Think of it as the heat transfer that takes place without contributions from friction. That is, there is no losses, there is no dissipation. It's the amount of heat transfer that you transfer just based on temperature difference. It doesn't involve frictional components. That's the internally reversible heat transfer that we refer to. We saw what is entropy. Entropy is defined as delta S is the entropy change in a cyclic process is delta Q internally reversible. Okay. If you have, I'll start again. If you have an internally reversible process, delta Q over T internally reversible is 0. The circle represents cycle in which initial state equals the end state, which means delta S is 0. Delta S itself is defined between two states as the heat transfer between the two states that is internally reversible. Okay, so delta S is S2 minus S1 is defined as delta Q over T internally reversible between state 1 to state 2. Okay, now I told you what is this Clausius inequality, which is delta Q over T is less than 0. I can split this for a process going from 1 to 2. I can split this delta Q from 1 to 2 delta Q over T, and then 1 to 2 delta Q over T reversible, this being equal to 0. Okay, so I can write this 1 to 2 delta Q over T, which is not reversible, plus S2 minus S1 being equal to 0. Okay, so I have 1 to 2 delta Q over T plus S2 minus S1 is less than or equal to 0. This is nothing but ds, or ds is greater than or equal to